Hello everyone, my name is Ossendrijver, and on behalf of my co-authors Stephan Schroevers and Clemens Grelck, I present to you the paper Towards Automated Library Migrations with Errorprone and Refaster. Stephan is from Picnic, it's an Amsterdam-based online supermarket, and Clemens is from the University of Amsterdam. Third-party libraries. Software projects heavily depend on third-party libraries. This happens to reuse software and make sure that we can deliver high quality software in a timely manner and therefore save costs, be cost effective. When we choose a specific library, we have requirements for that library, but over time a library may fail to meet these requirements or the requirements may change. Therefore, we periodically need to replace one library with a newer, a better, a different library. That process is called library migration. Library migrations are often performed manually, and they, especially for big code bases, they can be very complex, error prone, and time consuming. And for all these reasons, there's an immediate need for automation. In the context of this paper, we consider the tools error prone and Refaster. I'm going to tell you a bit about the tools. So error prone is an open source tool created by Google. It's a compile time static analysis tool, and it uses the abstract syntax tree to analyze your code and find bugs and anti-patterns. But it cannot only find those bugs, it still has a direct link to the source code. So you can also provide a suggested fix for a bug, which means that you can run error prone in patch mode, and then you can find the bug and you can fix it over your whole code base in one go, which makes error prone quite a powerful tool. But it also comes with a downside, because as some of you might have worked with the AST, it can also be quite complex to write such a check. For that reason, they created another tool on top of error prone, and that tool is called Refaster. It's also an open source tool, and it's a tool with which you can define refactoring operations using before and after templates. And you can define those refactoring operations using plain Java. So here I have an example of a Refaster template. What you see here is we have a before template where we say which expression we want to match. And in the after template here, we can say to what code we want to rewrite that. So for example, I here have on the left an example where you see a string expression in the condition of an if statement. So this is a string expression where we get that in the parameter, and then we can match. We only match if the equals is called here. Well, that is the case. And then we say that we automatically want to rewrite that to the dot is empty. So if we apply Refaster on the left here, we get the dot is empty. As you can see, it's quite easy to define such a refactoring operation, but the downside is that that Refaster only works on expressions and statements, which generally means only in method bodies or static initializer blocks. Yeah, let's dive into a running example that we use for the automated migration. So it's important to note that Refaster and error prone are tools to rewrite code, but not specifically meant to to support the automation of library migrations. So we have here two libraries, ArcJava and Reactor, and both are libraries that enable reactive programming. And ArcJava is a very popular tool. It has over 45,000 stars on GitHub, and Reactor is the new hot library that we want to migrate to. It's important to note that there exists an adapter which allows us to easily convert ArcJava objects to Reactor, and from Reactor we can also go back to an ArcJava object. Yeah, for the migration we have two parts. First, we want to dive into how can we use error prone and Refaster with the existing set of features to automate as much code, to automate as much of the library migration as we can. And then we heavily extend error prone and Refaster such that we can improve how much code we can automatically migrate. So let's dive into an example of how the migration from our ArcJava to Reactor looks like. At the top we have an ArcJava method, at the bottom we have the Reactor equivalent, and what you can directly see is that we have a single, and the equivalent of that in Reactor is a mono, and on a single and on a mono we have various operators. So for example the just, map, switch if empty, and there are equivalent operators of that in Reactor. But there are some exceptions. So for example, the flat map maybe does not have a single direct equivalent in Reactor. That is a problem because that makes the migration a bit harder. because we cannot simply use the structural search and replace in our EDA to replace every single occurrence with a mono, because then the code would simply not compile. Especially if we would just update the return type, and we here expect on a call side we expect a single, and then we just without really migrating we get a mono. That simply doesn't work. So we have to take some extra steps there. But the first question is, can we use the existing set of features of Error-Prone and Refaster for this? Well, no, we cannot use Error-Prone directly because there's simply nothing that helps us with, for example, migrating the return types. But we can use Refaster because we can make a mapping of the operators, for example. So let's dive into an example of how we would rewrite a single just to a monadal just with Refaster. Here I have a Refaster template where we say, hey, we want to match a single just. And we want to rewrite that to a monadal just, but not only a monadal just. We also want to wrap that expression in an adapter call statement, which means that we still have the resulting expression. The return type of the resulting expression is still of type single and not of type mono, because we need to make sure that we have compilable code after applying Error-Prone or Refaster. And why is that important? Well, Error-Prone hooks directly into your compiler. So after the compilation is done, Error-Prone can do its analysis. So if we would end up with non-compilable code, the code wouldn't compile, and we cannot use Error-Prone or Refaster anymore. So therefore, that is really important. Here you see only a mapping of one operator, but note that the RxJava API has over 1,000 operators. So we had to write a lot of Refaster templates to make this migration work. And now I'm going to show you a demo. And again, here the first part of the demo will be with the existing set of features, and then we'll quickly go over to the next part where we can run the rest of the migration using the extensions that we created. So yes, let's go to the code. Okay, so what we see here is we have an we have an RxJava method. So we see here a RxJava return type single, and we have a simple method with two operators, and here we call that single, and we also have an operator on that single. So the first step would be that we use the existing set of features, which basically means that we want to run Refaster templates to migrate the RxJava usages to Reactor. Well, and I here have already some predefined commands, just such that I can easily demo, but normally you can run all the steps simultaneously, and we can just run an automated migration. But now it's easy for the steps. So I just ran the first step, and we expect to see that the single just and the operators I just highlighted, that they will get rewritten. So here we indeed see that is true. So we have now the monadal just instead of the single just, but also wrapped inside the adapter call. But this is actually the first part of the demo, because we cannot do more than this with the existing set of features. So now I already run the second step, and the first step of using our extensions is that we want to make a duplicate. We want to duplicate the method, and here we see that. So what we now see is that we have the same method, but then with the migrated, and we have the Reactor return type, and this was the original expression. It's now again wrapped inside an adapter call. So the next thing what we can do is that we here have a double two adapter calls, which in the end yields the identity operation. So we can run Refaster to just remove that, but what you still can see is that this is the original method where we simply delegate to the new method, but then the call to that method is wrapped inside an adapter call. So the next step would be that we use an out-of-the-box provided feature by Error-Prone, which we also heavily extended to make sure that we can use it for the migration. And that is called the inline me feature, which is actually a deprecation mechanism. So what it does, I now run the first step, and what it goes over the code and it sees a deprecated method, and in this case it has one statement. And what this annotation then does, it says, hey, you can inline usage, if you call this method, so for example generate key here above, if you call me, you can instead of calling me directly, you can replace, here's the replacement, you can replace that with this expression, which is basically the body of the method. So the next step would be that we run the inliner, and then we now have to look at the generate key. And if I update, we see indeed that now this replacement is now put here. So we again can run the next step, because we now are not using the old ArcJava method anymore. We completely migrated to the Reactor equivalent, and we here have again two adapter calls, which yields the identity operation. So if I now click, we expect to see the generate key removed and this double conversion. And indeed, we now have the generate key and the old method is gone, which means that we now have a fully migrated class here. And yeah, we were, as you can see, capable of significantly pushing how much we can automatically migrate. Yes, so that was it for the demo. Now I'm going back to the slides. What you can see is that we, during the demo, I showed 2 of the 3 problems that we solved. So first we have the return types, the call sites, but we also have the interfaces, because if a method is defined in an interface, you have some difficulties there. You need to take some extra steps there, but for that I need to say please check out the paper on extra information on that. Then the validation. Now during the demo you saw it on one small class, but we actually run the migration validation on 2 big code bases. Both code bases have over 150,000 lines of code. We have an industry, a code base provided by the industry, and a code base provided an open source repository. And for the industry code base, this is a code base provided by Picnic. It's the platform containing the core services related to users, deliveries, and articles, for example. And the open source code base is from Gravity. It's an API management platform. Yes, this is the table with the results. So the first line is where you can see how much we were able to migrate using the existing set of features, so without our extensions. For the industrial code base, that means that we could migrate 63% of all our Java usages. And for the open source code base, this was 48%. And after turning on our extensions, and yeah, we wanted to see how much can we further, how much more code can we automatically migrate. Well, in total, we were able to migrate 90% of all our Java usages for the industrial code base, and for the open source code base, it was 68%. Important to note is that the focus of the extensions was on automatically migrating return types of method declarations. And for the industrial code base, we were able to migrate 99% of all our Java return types. And for the open source code base, that was 64%. If you look at the table, you might wonder, okay, why is there a significant difference between the industrial code base and the open source code base? Well, the biggest reason for that is that there's a big difference in the code styles, because for the industrial code base, there is a thorough review process, there is a code style to adhere to, and for the open source code base, this is not the case. So what you would see, for example, in the open source code base, that there were deeply nested expressions. And that prevented some Refaster templates from matching, and therefore cleaning up the code and removing ArcJava usages. And for the tests, we also had in the open source code base, there were a lot of tests that used local variables, and therefore we could also not use all our Refaster templates there. And yeah, those are the reasons for that. Then the conclusions. Well, we can now say that error-prone and Refaster are indeed suitable tools for the automation of library migrations, and that if you write, by writing extensions, we are able to further improve how much code we can automatically migrate. And we wrote the extensions for error-prone and Refaster in such a way that you only need Refaster knowledge to define a new migration, which means that you don't need you don't need to know how the AST works, how the internals of the compiler work, and so only Refaster knowledge for that. And then the contributions, we already did quite some PRs for features and improvements on the upstream code base of Google error-prone, and our framework to define these library migrations is open source, and so are our extensions. And we also open source the Refaster templates that we use to automatically migrate ArcJava to Reactor. Then the future work, I already briefly mentioned it in the previous slide. we want to improve support for local variables and parameters, such that we can also automatically migrate those. And we want to write more Refaster templates also for the ArcSample to reactor migration, because not all of them are there. And we want to contribute more code upstream to Google Error-Prone. And with that, I'm come to the last slide, and I want to thank you for your attention. I hope you enjoyed the presentation, and if you have any questions or want to discuss anything, please feel free to reach out. Yeah, thanks a lot.